In this video, I'm going to be talking about putting a linear system of differential equations into what's called normal form. So we actually saw this at the end of the last video. I just hadn't introduced this terminology. So let's start with the definition. A linear system of first-order differential equations has the following form. All right, so on the left-hand side, I have derivatives of functions, so derivative x1 and x2 and so on, up until xm, and each of these functions has the following form. So for example, x1 prime of t is equal to a11 of t. So a11 of t is some function of t times x1 of t plus a12 of t times x2 of t, and I keep going like that until I get to a sub 1 n of t times x sub n of t plus, and then there might be some extra function here, which I'm calling f1 of t. So I write out equations like that for each of these derivatives that I have. So the variables, the functions that I would be solving for are the x1 of t, x2 of t, up to xn of t. It's kind of like solving for x1, x2, up until xn when we did that in linear algebra, except now all of these aren't just constants. They're not just going to be real numbers, they're going to be functions. All right, so if we have a linear system, of equations that looks like this, I can convert this to matrix form, like we saw in the last video. So the left-hand side, if we put that in matrix form, would become a vector. It would be x1 prime of t, let me just go dot 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 at that point, up until xm prime of t. So that's what the left-hand side would become. And the right-hand side, so for this portion right here, this will be a matrix times a vector. It'll be the matrix that has a11t dot 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 up until a1, let's write that better, a1n of t. I'm basically putting the coefficients of the x1t, x2t, xnt, and writing those as entries in my matrix. So dot 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 down until am1 of t, dot 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 over until amn of t, dot dot dot. There is my matrix, and that's being multiplied by the vector that has entries x1 of t, dot dot dot, up until xm of t. And then we have one more vector for all these green functions, f1 of t, dot dot dot, up until fm of t. Okay, so I'm going to introduce some notation. This matrix right here, I'm going to call this capital A for a matrix, and I'm going to put a parentheses t because it's a function of t. Each of these entries is a function of t. This vector right here with all of these x functions, I'm going to call this x with a vector over it to indicate that it's a vector, and then I'm going to write t. All right, so if I follow that notation for that vector, this vector that has all the derivatives of the x's, I'm going to notate this as x vector prime of t. So when I see this notation, or I see a vector, and I see this prime to indicate its derivative, that means I'm taking the derivative of each of the entries. All right, and then finally this vector over here with all the f's, I'm going to call this f vector of t. All right, so using this simpler notation, I can write this equation as x vector prime of t equals the matrix A of t times the vector x of t plus the vector f of t. Okay, so we've rewritten our system into this matrix vector form, and this is what's called normal form. This is what's called normal form for our system of differential equations. So we're going to be focusing on a special case. We're going to be looking at the case where m and n are the same. So the number of equations, the number of these unknown functions that we're solving for, these x's, they're the same. Now thinking about that is one thing I didn't catch earlier. It's the fact that over here, when I wrote x sub m, I should have written should have written x sub n of t. And the reason for that is, on the right-hand side of our equation, we had x1, x2, all the way up until xn. So we had n of these sort of unknown functions. We only had m rows. Okay, so back to what I was saying before. So we're going to be looking at the case where m is equal to n. And if m is equal to n, that's going to mean that our matrix A of t is square. Okay, so we're mostly going to be looking at the scenario where A has constant entries. So these entries of A are going to be constant. And the situation where f of t, this other vector, is a zero vector. So this is going to be the homogeneous case. All right, so next what I want to do is talk about how do we let's practice putting systems into normal form. Let's do some examples. So let's write the following systems of differential equations as first-order systems in normal form. All right, so here is part A. So I have this system of differential equations. I want to put this into normal form. Okay, so how can I put this into normal form? So the left-hand side will become a vector, and just, to write it a little bit more shorter, I'll just call it x prime instead of x prime of t. And then I have y prime and then z prime. And this is going to be equal to, let's rewrite the right-hand side as a matrix times a vector. So the matrix, notice that on the first row, the coefficients as here, 3 for x, 4 for y, 5 for z. So I'm going to see those same numbers as the first row here, 3, 4, 5. So 3, 4, and 5. For the second row, the coefficients are, there's a -1 in front of the x, there's nothing in front of the y, there's no y term, and there's a 2 in front of the z. Okay, so writing those numbers down, I have a -1 in front of the x, 0 in front of the y, 2 in front of the z. So -1, 0, and 2. And then finally, for this third row, nothing in front of the x, 7 in front of the y, and -3 in front of the z. So I get 0 in front of the x, 7 with the y, -3 with the z. And that's going to get multiplied by the vector x, y, z. Okay, and now let's write this in even more condensed format. So I'm going to call this whole thing just my vector, x with the vector on it. So what we have is, we have x vector prime on the left-hand side, and that's equal to this matrix. So our matrix is 3, 4, 5, -1, 0, 2, 0, 7, -3, times the vector valued function x. So and I need to say what x is. So x is the vector that has the functions x, y, and z as the entries. So notice that when I write x with this vector arrow on it, that means something different than when I write this x here that doesn't have the vector on it. So this x is what's called, with this vector on it, it's called a vector valued function. That means two things. It's a vector, and each of the entries is a function. All right, so this right here, this was, oh, whoops, let's box that as well. This was our answer. Let's do another example. So here is part B. So I have this differential equation, just sort of one differential equation, y double prime minus 4y prime plus 3y equals 0. But even if I have one differential equation like this, I can put it into normal form. But one thing that I might notice is this differential equation has a second order derivative right here. So to be able to handle this, to be able to put it into normal form, I need all my derivatives just to be first derivatives. So we need to write this as a first order derivative to be able to do this. So the idea for that is, notice that y double prime is the first derivative of y prime. All right, so now what I'm going to do is, so this is going to seem kind of new and maybe a little bit out of the blue, but it'll be really important in terms of, expressing everything in terms of just first derivatives here. So I'm going to let x, my vector valued function, be, a vector where the first entry is the function y, and the second entry is the function y prime. So I need this vector to contain the original function and all of its derivatives up until one below the highest order that I see. So here I see order 2, so I go up until y prime. If my differential equation had been order 10, then I would have kept going until the 9th derivative of y. And the reason that I want to do that is, by setting it up like this, I'm going to be able to express all of these higher order derivatives in my differential equation as a first derivative of the thing sort of below it. Like the second derivative is the derivative of y prime. Okay, so what are we going to do with this now? So let's now take the derivative of this vector valued function. The derivative of vector x prime is going to be, I have to take the derivatives of each of these, y prime and y double prime. All right, so y prime, I'm just going to leave it how it is. For y double prime, I can isolate y double prime in this equation. And if I were to do that, y double prime is 4y prime minus 3y. Okay, so we have sort of, expressed this higher order derivative in terms of the lower order derivatives that I have. All right, and now what I'm going to do is I'm going to put this in parametric vector form. So this is going to be y times the vector 0, negative 3, plus y prime times the vector 1, 4. So now I can put this into matrix vector form. I'll have the matrix 0, negative 3, 1, 4, times the vector whose entries were the weights of this linear combination. So it was y first and then y prime second. Okay, so what we have now is we have the matrix 0, 1, negative 3, 4, but notice that the vector x that has y and y prime as the entries, that's what's showing up here. So I can just express this as multiplying by the vector valued function x. Okay, so what this gives is it gives us the equation in normal form. So x prime equals the matrix 0, 1, negative 3, 4 times the vector valued function x. So when I put something in normal form, I always need to put it like this. And then say what x is, where the vector valued function x was y and y prime as the entries of my vector. And that is our answer. So I want to end with kind of a cool fact about the original differential equation and this matrix form of it and how they're kind of related. So the cool fact is to note that if we were to look at the auxiliary equation of our original differential equation, y double prime minus 4y prime plus 3y equals 0. Its auxiliary equation is r squared minus 4r plus 3 equals 0. So sometimes we call the auxiliary equation the characteristic equation. And it turns out there's a connection between the auxiliary equation of this single differential equation like this and the characteristic equation of its matrix in normal form. So this connects with the characteristic equation of the matrix we just got, 0, 1, negative 3, 4. If we were to find its characteristic equation and look at the determinant of a minus lambda I, we'd end up getting, so this 0 would become a negative lambda, and that would multiply, the 4 would become 4 minus lambda, and then we'd get minus negative 3 times 1, and this needs to be equal to 0, and if we simplify this, distributing negative lambda, we'll get lambda squared, we'll also get minus 4 lambda, and then this negative 3 becomes a positive 3, and that equals 0. So notice that our characteristic equation of this matrix once we put it into normal form, is exactly the same as the auxiliary equation or the characteristic equation of the original differential equation before we did anything to it. So that is one of the reasons why this auxiliary equation is called what it is. It's sometimes called a characteristic equation.